So I think we stopped at SMEFT. So we did the classification of effective field theories. Just to revise ourselves, because so we were doing this. So we said there is something called SMEFT, and this, how do we classify effective field theories? Degrees of freedom, symmetry, scale of the problem. Okay. So degrees of freedom, symmetry, scale of the problem. So that's how we classify. But all the symmetries which we are talking about, all the effective field theories we are talking about in this course are related only to standard model. Okay. There could be other effective field theories, meaning I don't know how many of you attended Rohini's conference or something. There was this question about how to use heavy quark effective symmetry, and there was also this question about soft collinear effective field theory, and so on, so on. Okay, so the degrees of freedom are standard model particles for SMEFT. The symmetry is just SU3C times SU3 times U1Y, and the scale is much greater than or MW square, essentially, which is scale is much higher than the weak scale, essentially. That's the only thing, one order of magnitude. What is the, why is the mass difference? Why is the mass difference? Because the same thing, but loop corrections can modify it because of the non-zero CKM matrix. If CKM matrix is unity, then the mass difference is 0. As no, it's the mass difference comes purely from loop effects. Delta mk is generated by loop effects. You cannot calculate k0 mass by just adding the these things. There are long distance effects and everything. Okay, so but the mass difference is essentially, okay, if you want to put it in a, you have observed this mass difference. If you ask the fundamental difference, why there should be an antiparticle and particle of different masses, that means their CP invariance is broken. Okay, you are asking that. How do you calculate? I was saying essentially. Okay. Okay. No. Yeah. So it's a bound state. Okay, that's another. But CP invariance is broken. If you have some other particles, say for example, neutrino and antineutrino have different masses, then you have to invoke CPT invariance. Okay, CPT invariance insists that all the masses are same, the masses particles, because neutrinos can be Marana as well as Dirac. In this case, I think just CP invariance is sufficient, K0 and K0. Yeah. You can theoretically. No, fundamental particle. Okay, there is something called the CPT theorem. So neutrinos are fundamental. That's the reason why I was telling him the example of neutrinos. So there is something called the CPT theorem which has three assumptions. So one of them is Lorentz invariance. Local interactions. And third one is called hermicity. So hermicity meaning the Lagrangian need not be Hermitian. So if you make these three assumptions in any quantum field theory, the quantum field theory tells you that it is CPT invariant. Okay. So you have a particle state CPT, apply CPT, you apply CPT. Okay, some state essentially chi, say for example, in field theory. So if you make these assumptions, CPT is conserved. Now one consequence of CPT breaking could be that particle and antiparticle will have opposite masses, I mean different masses. So one of the consequences, chi and chi bar have same mass. Okay, the Hamiltonian is the same and everything essentially. Now once, how do you break CPT? In quantum field theory, you violate one of these rules. Okay, you violate one of these assumptions and then you get masses which are different for particles and antiparticles. But this is sacred. Huh? The CPT theorem is super sacred. They are not fundamental particles, number one, essentially. Okay, and they break CP, not CPT. They break CP. Okay. In field theory, it's you don't write they're bound states, right? Essentially. So bound states can have different masses. You can imagine it. But an individual quark, which is a fundamental particle. Okay. Positronium. Positronium. Yeah. Okay. Say for example, any positronium. Take for example, there have been searches for positronium, CP violation in positronium, but that will be much smaller because the effects of the CP violation in that system are very small, very tiny because they will be suppressed by the neutron mass over MW mass square. Okay, they are very small. Okay, in the case of a bound state like K0 K0 bar, essentially, the short distance effects can be large because the intermediate particles can be heavy. That's the loop you calculated, the boxes essentially. Okay, their effects can be large because the phase is carried by the top quark mass essentially. No, mesons are always one quark and one anti-quark. Always. Okay, right. Yeah. It's not the same, right? It's not the same. That's the entire point of CP violation. They are predicted to the same if you take the phase to be 0. There is a phase in the CKM. Okay. They are not the same. That is the reason why you get an imaginary component in that. If you calculate fundamentally in the Hamiltonian, in the effective calculation, so there is an imaginary component essentially. First of all, that's because they are decaying, and also because you have a phase in the CKM matrix.
I assume the initial and final quarks to be free.
That is short distance. Yes, when you are calculating the short, that's not correct, but you are not leaving it there. That is just a short distance. How will you deal with a bound search system? So you say that there is some sort of factorization that you can factorize the long distance effect. I think you were missing all the classes. That's the reason I mentioned it several times in the class. Okay, the short distance effects are factorized out, and you can calculate it, and then you multiply it with the long distance effects. Last 3-4 classes I have been mentioning this only essentially. So you decompose the short distance effects and long distance effects. What you are calculating at a short distance, you are calculating with, it's not, it's completely purely, I think I did the entire steps of the calculation. So what you did at the short distance effect, you are using SM. But when you are calculating the long distance effects, so you don't use SM anymore, you have to put it in terms of the quark fields, the mesonic fields. So there you use another effective field theory at a much lower scale. Okay, you use another effective field theory, and there are a different set of effective field theories. There are 2 different effective field theories running at play, and in fact in the K0 K0 of our system there are 3 different effective field theories which are playing in today. One is the LEFT, one is the and mapping of the LEFT to chiral PT. Okay. Okay. Yeah. Yeah, you had some question essentially. Yeah. Okay, I think Deep was asking this question. So I did last class entirely on the same thing essentially. Okay, the same question was asked by Deep essentially. Yeah. It violates a lot of stuff. Yes, yes, yes. You need Lorentz invariance for CPT. Now, the point is that, say, if you break Lorentz invariance, you have 2 sets of operators. One are CPT odd, and some of them are, if you classify all possible operators. Okay, Lorentz is a necessary condition, definitely for CPT invariance, but it's not sufficient. And what I meant to say is, it's not necessary that all the CPT odd operators will break Lorentz invariance, but there could be Lorentz invariant breaking operators which are CPT even also. Okay, so let me just complete this 1 second. Okay, Lorentz, you break it, you have CPT odd, CPT even. Depends upon if you just take 5th dimension or 6th dimension as infinite and you are not breaking Lorentz invariance, then it's always there. But if you break the momenta of the 5th dimension by compactifying or something, okay, or there are also, you put in something called you do a lot of stuff. Essentially, you put some currents inside the 5th dimension and then encloses it essentially. So there are all possible. Then the Lorentz invariance is obviously broken in the sense of it will be more like GR rather than You don't take it in terms of 4 dimension. The moment fifth dimension starts coming in, you have to worry more about GR like theories. So diffeomorphism invariance and those things will not be there, but yeah. Anything? Are you satisfied that you can differentiate between that two? So uh, the degrees of freedom are different at different scale. At long distance, there's a different set of degrees of freedom. At short distance, you have different. So that's the reason when you are doing K0 K based oscillations, you are just using quantum mechanics. Okay, and just using M and I, there is a Hamiltonian which you write down. You are not putting it connecting with short distance effects. Okay, there your quantum mechanical states, you run them, do the oscillation phenomena, and get to the oscillation everything essentially. Okay, with the decay rate delta gamma and everything. Okay, but the moment you start to calculate what is this delta M, then it can go to any field theory, okay, in a short distance theory, in a UV theory, then you have to do the matching with a UV theory, which could be SM itself, which is SM itself. So one is SMEFT. So then we have left or low energy effective field theory. So low energy effective field theory has not all the SM particles minus top Higgs W C. You remove these particles, integrate them out, then write down all possible expansion in with those operators. And what is the symmetry you have here? So this is a broken thing. Okay, there is one more thing which I have to mention. Depending upon the mass scale of the problem, essentially. In this case, I should also mention that Higgs is linearly represented. Okay. There is another equivalent class of theories, I think, which was also discussed, called Higgs effective field theory, in which all the SM particles are there. Higgs is the Higgs representation is nonlinear under the SU2 essentially. So what does nonlinear and linear mean? I have mixed groups. No, what has this to do with it? Is the same thing, right? Okay, one is a linear sigma model, another is a nonlinear sigma model. In linear sigma model, the Higgs is realized. Okay, the expansion is so G1 plus G2. So these are your Goldstone modes, and this is in nonlinear sigma model. You don't have a linear mode essentially. So here you have, okay, here you have Higgs mode essentially, which is effectively replaced. So, but you can always assume that in nonlinear mode, you write the Higgs field expand it in terms of an exponential essentially. Okay, you expand it in terms of an exponential. Okay, the Higgs field as expansion as an exponential. So V by F or something. Okay. So you have everything in terms of this nonlinear mode. We can write V or we can write phi or whatever it is equivalent. So this is like a nonlinear sigma model, whereas this is like a linear sigma model. Okay, I'll give you one more assignment just to do linear and nonlinear sigma models. These are important essentially. Okay, but the most important things. So, okay. Yeah, I think it's better to write the phi. So, in terms of the theory space or the field space, HEFT is much larger. And then there is the SMEFT. Because the first term in this will give you back the linear mode. The higher modes are not possible. Higher expansion terms are not. The first term is just a linear expansion essentially. F is some constant essentially, like a pion decay constant essentially. So you can call it as the Higgs decay constant or something. Okay. So HEFT covers much larger regions of the parameter space where Higgs could be a composite particle. In a linear theory, Higgs is not a composite particle, it is essentially a fundamental particle, it is there. Whereas in this theory cases, HEFT, Higgs could be composite, it could be like essentially like a pion, it could be a Goldstone boson of some higher symmetries. Okay, so composite Higgs models and all these things will come into the play. Okay, now the symmetries are roughly the same, they are roughly, except that the representation of the Higgs is non-linearly realized here, whereas it's linearly realized. The scale is also roughly the same. In low energy effective theory, on the contrary, you don't have the SU2 symmetry, you only have SU3 and U1 because it's in the broken phase of SMEFT. Okay. In addition to broken phase of SMEFT, you integrate out top, Higgs, W and Z. All the gauge bosons are integrated out. So what is the gauge boson which is left in LEFT? Gluon and photon. So if you take low energy dark matter particles below GeV or something, essentially, you have to write a photon like interaction for them essentially in principle. Okay, so this can be valid all the way up to the scales which are close to MB and MK essentially, where another field theory will take over, which is like chiral PT or lattice gauge theories, they will take over essentially. Okay, so we have introduced 1, 2, there is HEFT, then there are other things, chiral PT. So this is valid at a scale which is lambda . Now depending upon the symmetry, so there are two kinds of Carroll's theories. So you have UDS, which is a chiral symmetry of SU3L times SU3R. This is a flavor symmetry. This is not color symmetry. This is a flavor symmetry, 3 quarks. This is not internal symmetry, it's a global symmetry. It's not a gauge symmetry. Okay. Then a lower version which works for pions very well. So this was built on current algebra by Gell-Mann, Weinberg and other things, and then later on built on by Lott-Wheeler, Gasser and completely essentially to make predictions. And in all these things, in all these theories, you can do one loop calculations, one loop effective field calculations. So this stops around 1 GeV essentially. Yeah. Now you want to match this theory with this theory. You want to match this theory with this theory if you want to make predictions. Say for example K0, K0 bar. Yes. Around 1 GeV roughly. 200 mGeV is not very strict, see. So it depends upon how you connect it with phenomenology. Okay. 200 mGeV is not, okay, 220 or whatever they say, no, lambda QCD. Okay. This is not very strict essentially. Okay. So already alpha S becomes very, very strong at 1 GeV. Yeah. Yes.
That sort of giving us an effective voltage to calculate things maybe easily.
Right.
But in SMEFT, we have all the same particles. So
Yeah.
the use of SMEFT only for BSM physics or it also for standard physics?
In a way, whether SMEFT can be used for standard model physics. As I will tell you today, SMEFT it's actually useful for only for BSM physics, because what it does is it modifies all the standard model predictions. Are there any cases? Yes. Right. It doesn't come purely as SM, that's the point. In SM, there are no corrections to the couplings. Let's take gluon coupling. Gluon coupling, there are certain cases, if you go, no, you're right. Essentially, that it's only for BSM. So, for example, gluon coupling, what is given in standard model is, we know what it is, even at one loop also. You can write an effective vertex for it. But even this effective vertex get corrected. Just looking, say, some standard model higher order corrections can be represented by SMEFT operators. But in that case, they cannot take any value they want. They have to take a very specific value. But if there are free parameters, okay, then they are SMEFT, they are BSM physics. Okay. So, for example, yeah, so gluon coupling will get modified at one loop, say for example. But then when you write the gluon coupling at one loop in SMEFT, there is a correction in SMEFT. Now, if that coupling can arise from standard model operators itself, but then it will have a very specific value for the Wilson coefficient. Okay, because you can calculate it in standard model. Okay, but that is no longer true if you take it as a free parameter, as a Wilson coefficient. Then it breaks gauge invariance of SC3 and everything. So it is a signature of BSM physics. Yeah. Yeah. So this is a classification which we are looking at, and okay. So I'll just sketch this thing, same thing again, because of all the questions, I realized that many uh, of you have not understood the basic philosophy of effective field theories. I am repeating this. I told it already in 2 classes, but I am repeating it again because this example really shows the philosophy of effective field theory. So let's take K0 K0 bar again. Okay. There are 2 diagrams. Now let's worry about one diagram. Okay. You can flip it. You can get the other diagram. Now this is D S S S D. Okay. DS and SB. Okay. Bar. I'm putting it. Right. Don't worry about the bars because the fermion line is going on the opposite direction. Now, how many scales are there in this problem? There is a scale which is very short distance, which is happening inside, deep inside the kaon. Okay. Now, what is the kaon mass? This we discussed several times in these lectures, but anyway, how many people can tell me kaon mass again? Anand, last time also you checked. Yes, exactly, around 497 or something essentially. So kaon mass if you add the individual quark masses, nowhere that individual quark masses, if we add it, it will have come out to be 100 MeV. So this is a particle which is dominated by long distance effects. Okay. So the mass difference K0 K0 bar mk delta mk by mk is 10 power minus 5, 10 power minus 6. It's around that. Okay. It's around 1 million% essentially. 1 per mil. 1 per mil. Now, how will you deal with this problem? This is a place where you actually have effective field theories. Now you say that you can separate the short distance effects, meaning the short distance meaning what is happening at the much below the Fermi level, where there are this thing. Okay. So let's start with standard model. So you start with LEFT. Okay. To begin with, you start with SM. But before SM, you have to distinguish between short distance effect and long distance effect. Short distance effects, what are the degrees of freedom you have? Only D and S. And what are the symmetries? There is no standard model symmetry. W symmetry, what are the symmetries? Only QCD and electromagnetism. With this, you write down all possible operators. So you only have 2 fields, ds. Forget about long distance. I am still doing the calculation at the short distance. ds and all possible operators. You don't. So this part I am giving interpretation as standard model. Forget about that there is a standard model. Forget that there is a standard model. In a low energy effective field theory, how will I deal? K0 has D and S. Something is happening to them and it is getting converted into S and D. So I'll write down all possible operators for D and S. How will I write down? What are the symmetries I have? I have Lorentz symmetry, SU3 and EM. Okay, SU3, Lorentz symmetry, So at the effective theory, field theory level, you completely forget this. You don't have these degrees of freedom. I'll come back to that when they will come essentially. So then you write down all possible operators. ds bar, sd bar. This is your, okay, you can write it like this. So then you can put, and you put a coefficient C1, C2 by lambda square. Now you can put a gamma 5. Then C3 by lambda square, you can put a gamma mu. These all dictated by Lorentz symmetry, nothing else. I don't know what is happening inside. I don't care what is happening inside. Okay? And then you write down all possible operators, C7, S bar sigma mu d, F mu nu. You can write F mu nu, or you can write S bar sigma mu nu d square. Okay, the other one. Then you can also write a chromomagnetic operator. So just like an electromagnetic operator, you can write a chromomagnetic operator. You write down all possible operators. 9. Fit the data. You fit the data. You are not making any contribution to the standard model. Now you take these operators, one by one you put it in effective Hamiltonian. K0 bar. Calculate this. So you get some Fk times some which are the relevant operators which are there, which will contribute. Only those set of operators, you can take one operator at a time or two operator, whatever it is. Okay. Only then some C1 square or something will come. Then Mk square, some 16 pi, whatever, some term will come. Coefficients of Wilson coefficients. So what you have now, this Fk is a long distance effect. So what you are doing, H effective, short distance. Now these wave functions are long distance wave functions. You are mapping them. Now here you can map this L effect, H effective operators. If you are not sure of K0, you have to calculate these wave functions, right? This mapping can be done in parallel PT or lattice. Lattice tells you, if you given an effective theory, how this mapping happens to this. It gives you this matrix element. Lattice or chiral PT will give you this matrix element for each operator by operator. H effective is this is short distance, because you are writing in terms of the quarks. This is your H effective. Higher energy. This is high energy. K0 bar is long distance. Remember your QCD. You remember your QCD. QCD is always long distance. Bound states are always Fermi level, whereas weak interactions and everything are at 2 orders of magnitude shorter at higher distance. Okay. So this is your first effective field theory calculation which you do. Okay. Now there is no standard model, there is no SMEFT, there is nothing here. To LEFT, the UV theory is standard model. So in standard model, you calculate this box, then you calculate this box in standard model, then match it with LEFT or HFT, match it, and then tell which of the operators are valid in standard model, which are not valid in standard model. For example, you don't have right-handed currents in HEFT, in standard model. So you can write all possible operators with even right-handed currents. Okay, they may not contribute in the standard model. So what you have essentially is this thing, these Wilson coefficients. Some of these Wilson coefficients come from standard model. So when you take these Wilson coefficients to be calculated in the standard model, then you call them as standard model prediction. Then match it with experiment. Then you say, okay, there is an anomaly, there is an anomaly or whatever it is. Then immediately you say there is another operator which is contributing. There is another operator which is contributing so that the anomaly can be compensated, but you don't, and that operator can come from some other new physics or something else. Okay. So at the level of just doing the K0 K0 bar physics, you only have two effective field theories. One is this LEFT or H effective or whatever it is, and chiral PT or lattice. This is the only thing you use. You are not even using standard model unless you want to do a standard model prediction. Unless you want to do a standard model prediction, won't do it. Pardon? What is the physical? It gives you that the transition amplitude, right? You have not done your homework. That is a transition amplitude between K0 K0 bar. These states oscillate. That's a exponent signal. Now this need not be. I think last time I gave another example, BTS gamma. Okay, there is another which is a well-known process. This is a penguin. K0 K0 bar is a box. Okay, and there is a spectator quark sitting here, D. It turns out, if you write the effective field theory, same bunch of operators, but instead of B and S, you write B and D. Okay, instead of B and S, you write B and D. And S, there are three of them. Okay, but all the relevant are B and S. This is just a spectator, it's just sitting there, so it's not doing anything. So the degrees of freedom you change to B and S transitions. Now B and S transitions can be many places, not only in B to S. Okay, there could be B to 5K short, B to K, so many processes are there. For all of them there is only one effective field theory. Yes. So all of them there is only one effective field theory. Okay, B to BS BS oscillations. Just like K0 K0 oscillations, there are BS BS oscillations. There is BD BD oscillations. Okay, for all of them there is only one effective field theory. You write them down. For each process you do this matching and fix the corresponding matrix element. Fix the corresponding matrix. Okay. Okay, there is only one effective field theory, and then instead of chiral PT in the B physics, you use heavy quark effective field theory. This matching, final matching, when you do this with B systems, you don't use chiral PT because it doesn't work. You use heavy quark effective field. One, what FK was coming from lattice or chiral PT or some, or a mixture of both of them. FK is a constant. It is determined by chiral PT. It's same. The same. It's a constant which appears in various places. It's just like it's a k-on decay constant, like pion decay constant, same. Okay, in chiral PT also you can write something like a k-on decay constant. In each of these operators, the final thing you may get Fk times some other Lorentz structure, okay, some other Lorentz structure, some other constants, but Fk would be typically be there essentially, times the mass of the k-on or B mass or something, and some coefficients which will be different, and depends on, so if it is BTS gamma, it's a boosted in because it's measured in, say if you are measuring, whether you are measuring in E plus E minus colliders or if it is measured in LHCb, it makes a difference for the prediction, and how much you, whether you see the photon finally or not, what is the threshold of the photon, everything makes a difference because it has been computed at a very high precision. Then there are QCD corrections on it. Okay, whereas, but the philosophy of effective field theory is you don't care about the UV theory at all. You don't care about the standard model at all. You write down all possible operators given by the symmetry. Okay, only when you want to match it with the standard model, you have to worry about the standard model matching. This is the philosophy of effective field theory. Pardon? You only know only the C coefficients. You can only, yeah, it's not predictive in that sense. That is true. That's the fallacy of effective field theories. They are not predictive. So this is a philosophy you should. No, you can only, so each Wilson coefficient will have its Lorentz structure. Each Wilson coefficient will have its Lorentz structure. Lorentz structure we know, meaning whether it is scalar operator or whether it's a current operator, gamma mu operator. These are the only things which we know about it. But if we don't know its value, unless we match it with SM. Why they should be dependent on each other? Why? Why they should be there? They are completely independent. They are completely independent. Unless you have some background theory which predicts two operators to be same, at the effective field theory level, there is nothing which tells you that any two operators will not be the same. The expansion is completely free. So let's do SMEFT. Little bit more. So it has all SM particles and scale is much larger than MW, MZ, M Higgs, M Higgs. And the symmetry is GSM. So you should write down all possible operators without restricting to dimension 4. That is your assignment. Okay. That's all is the definition. Okay. The first one who did it was called. So you have L SMEFT, LSM plus L5 plus L6, 7, L8. Okay. So standard model L5, L6, L7, L8 means these are dimension 5 operators, dimension 6 operators, dimension 7 operators, dimension 8 operators, and so on. Everything could be possible. Everything. There is no symmetry which can stop it essentially. So the only symmetry which is possible is this symmetry. So the number of operators keeps increasing very fast, okay, with each dimension. Okay. So now the point is that how do you construct all these operators essentially? How do you construct all these operators? Now typically people avoid dimension 7 because most of them are baryon number violating and lepton number violating. Odd dimension operators are typically end up being baryon or lepton number violating operators. Okay. For example, dimension 5 operators L5 is a lepton number violating operator which forms a operator which is called LH square essentially, or LH. So the point is here is that lepton and the Higgs have identical quantum numbers, okay, except that one of them is a scalar, another is a fermion. So you can combine both of them to form a singlet, okay, or a triplet. Okay, you can form either of them, but if you want to make a scalar, you can make them in terms of two singlets essentially, okay, because you need two fermions, two scalars. Okay, so you do this and you get this operator essentially. Okay, so this is called dimension 5 operator, also called as Weinberg operator. Because Weinberg first discussed this in the 70s, okay, as a way of generating neutrino masses, okay, where lambda is close to gut scale. Turns out to be correct essentially. So the first people who tried to unify the gauge couplings was done by a very famous paper by Helen Quinn, Weinberg and Howard George. Okay, three of them, Queen, Georgia, and Weinberg, essentially. So later on, Weinberg, based on that, and in fact, if you see the last talk of Weinberg, I don't know if you all know this YouTube channel called All Things CFT, which is now stopped. The YouTube channel, it was running very well. Should look into it. It's very nice. It has a fantastic set of talks. It was running during COVID. They had two seasons. First season was started by Weinberg because, in many senses, people consider him as the father of effective field theories, essentially. Okay, so his talk was wonderful. He holds this thing that talks about unification scale. He talks about they all will lie there, and he was still teaching at that time. Essentially, this was just 1 or 2 years before he passed away. Essentially, okay. Now the second set of operators are dimension 6 operators. They are mostly 4 fermion operators. They are classified essentially. Various classifications, LEFT. So SMEFT, what people call SMEFT, most of the time these days, they are concentrating on dimension 6 operators. So what typically they call as dimension 6 operator or SMEFT is called um, wholly so holds of. Okay. Okay. Now the technique, how many operators are there? There are many operators, roughly around 2000, I think 2499 or some such thing. And they are typically written, they are basis dependent. And typically written in something called the Warsaw basis. So why they are basis dependent? Because not, it turns out that if you write down all possible operators, there are 2500 or something, out of which people when they do SMEFT, they only consider 20 or 30 because they further impose okay, why people, if you impose flavor conservation, okay, and baryon number and lepton number conservation, the number of operators falls down drastically. Only relevant operators would be around 20 to 30, essentially 22 to 23. And depending upon the set you are interested in or the phenomenology you are interested in, you only consider them. So flavor means SU3. Okay, SU3 flavor. How many flavor groups are there? There are 5 flavor groups. Okay, left-handed. Okay, so flavor symmetry imposition. This we studied early in the class. You must have forgotten, but I'll remind you. SU3 for all the left fields, SU3E for all the right fields, SU3Q for all the left fields, SU3U for all the right uptype fields, SU3D for all the right down type fields. So there are 5 flavor groups. You impose all of them. Okay, that means you say that any operator with uptype quark or a charm quark or a top quark is the same. Okay, There is no flavor violation in SMEFT. Okay. Then you impose baryon number U1B. Baryon number you know defined, right? For quarks, what is the baryon number? 1. 1/3. Right, very good. I was afraid you said 1. Okay, very well. Okay, baryon number. And then there are 3 lepton numbers. All this you impose. Then the number of operators drastically falls down. Now, but still doesn't answer the question why there is a basis dependence. Basis dependence comes from using something called the equations of motion. So the entire point of this Warsaw group was, so this first analysis, the first people to write this, all possible operators up to here were Buchmuller and Weiler. He is the same Daniel Weiler who comes to our department regularly every year. Okay, he wrote a very famous paper in '86 essentially that has thousands of citations. Started the SMEFT business completely. But what they had was more number of operators because they were not going on shell. So what Warsaw group pointed out that by using equations of motion, okay, at least 6 to 7 operators, 6 operators can be removed from the by using equations of motion. There is no recounting of these operators, meaning double counting of these operators essentially. So 6 operators can be redefined or removed by using equations of motion, and this is where basis dependence comes. Which 6 operators you remove? Okay. Nowadays it's called field. It's all rephrased in terms of field redefinitions. You can look at Timothy Cohen's papers on it and everything. They are very hard to understand, but okay. But they are asking a much detailed question essentially, that what is, how do you define the parameter space of SMEFT compared to HEFT? Can you distinguish between HEFT parameter space and SMEFT parameter space? So on, so essentially, those are difficult questions to come. So anyway, these 6 operators can be removed by using equations of motion. So using these equations of motion, it becomes basis dependent. So these 2499 operators are in something called as the Warsaw basis. They are also called as the Warsaw basis. So how do you write this, construct all these possible operators? Let's look at SMEFT at dimension 6. Let's not worry about dimension 8, but we'll come to dimension 8. These days it's becoming important one by one. So dimension 5 we have seen, dimension 6 we'll see. So let's take one interaction in standard model. Say top quark gamma mu lambda a, top quark g mu a. What is this of? This is lambda a means SU3. Top quark, 3 colors of top quark. Okay, you can be top left or top right, it doesn't matter, because QCD is chiral vector theory, not chiral theory. Okay, so you can write this operator. Now this operator is dimension 4 operator. Take this operator and this operator in SMEFT, you can write a corresponding operator by multiplying another gauge invariant quantity which is dimension 2. So what is the gauge invariant quantity which is dimension 2 in standard model? Which can only be made, which is a scalar, which is the only possibility. Excellent, excellent. That's it. You have dimension 6 operator. There is no other operator you can write down. You cannot write gauge bosons. They are all vectorial. They are not scalars. F mu is gauge invariant. Okay, but F mu square is only Lorentz invariant. But then it's dimension 4. Okay, dimension 2 level, which is the only operator in standard model. There is no other dimension 2 operator in the entire standard model Lagrangian except v square h dagger h. Can you think of anything? Okay, so you divide the mu square downstairs and you get this particular thing essentially. So this way you take any SM operator, multiply with phi dagger phi, you have SMEFT operators essentially. So what does this do? Now h dagger h goes to h plus v whole square by 2. So this becomes, this operator contains now. So what you can see, one of them is a dimension 5 operator, one of them is a dimension 6 operator in terms of the Higgs field after in the broken basis. Okay, but then there is a correction to dimension 4 term which is v square by lambda. So alpha s of the standard model becomes alpha s alpha s SMEFT becomes alpha s standard model plus 1 plus some constant c, because we had to write it with some constant c, Tg CTG v square by lambda. T is for the top quark, this operator, G is for the gluon. So in SMEFT, the first thing you see is that in the broken basis, you have corrections to all the couplings. You can write it for all the couplings essentially. Okay, every correction, all the couplings will get corrected by some v square by lambda square term. So this CTG or CT whatever, C gluon or coupling of photon or W or Z will always be correct, meaning should be very very small such that you get your whatever you measure in the standard model to be accurate essentially. So there will be a very strong constraint on this coupling, any modification of it. Now this is gauge invariant, yes, because we started with gauge invariance. Okay, but you change all the couplings without breaking gauge invariance. But the experiment, is it experimental invariant? That is the question essentially. Okay, it's not experimental invariance essentially. Huh? Alpha S. Alpha S you measure in various places. E plus E minus colliders. I think in the first few classes. So E plus E minus, low energy with neutrino scattering. Okay, wherever there is a gluon contribution. Okay, there yeah, there are various hadron collisions also but we need EP collisions mostly. So alpha S and structure functions are measured in so all the process in which there is this for example alpha S measured in LEP, it's inferred essentially, it's coming from BB. E plus E minus is going to BB bar, say for example. You measure the cross section very well, okay, and the BB bar will have corrections coming from alpha S essentially. Okay, so then now this is the coupling of the fermions to we have bounds, not yeah, depending upon what your lambda, you have bounds. So at 1 TeV you can estimate what is your alpha S. I think it will become 1.1 change, 0.99 or something. I still remember these numbers very well, but now I don't remember. But you can calculate it, and that is the standard model value. Now, if you so on the error bar of that, you put a limit on. Depending upon the lambda. Now, people can play on the ratio or what is the lambda value. So, people assume, some of them assume lambda is equal to 1 TeV and put limit on C. That's a game. Now, you can take G mu A, G mu A, this is the gluon kinetic function. Okay, gluon kinetic function. Now, again, this is allowed. This is allowed. This is a gauge invariant term. Okay, multiply. So the kinetic function of the gluon is modified. Okay. Now G mu is what again? Remind me. Del mu G mu minus del mu G mu minus I G. So this gives you the kinetic function. This gives you the kinetic function. But then if you put h dagger h, so the gluon functions are not canonically normalized. So what you call a gluon, if you want to write a gluon propagator in SMEFT, you have to recanonically normalize. Okay. So this h dagger h is equal to what? Again, h plus v whole square by 2, that is v square by lambda square, right? V square plus 2vh plus h square. I am using the same h for both broken and unbroken base. Okay, just that's my laziness. So this is not 1 anymore. Okay, this is not 1. So gluon fields so this will also lead to new effects, new vertices, where you have an operator GGH operator essentially, which is derivative, but it's also possible. New vertices will have. Now this GGH is generated. This is answering your question. In the standard model by this loop diagram. Okay, but this has a definite prediction. Okay, but here you are writing an arbitrary operator here essentially. In front of it you are putting some operator here, some C HG, which can take any value, arbitrary value. So it cannot, in the standard model it cannot take any value, it is a definite value. Okay, but if you are putting some CHG for this vertex, okay, it's a different thing essentially. Yeah, that's what you wrote, right? This is gauge invariant, that's what you wrote. Expand it. So there is a derivative, there is some p mu factors. Okay, v square by lambda square p mu plus p mu prime, maybe minus sign, I don't know, because there are two derivatives. So this is the vertex factor you can derive for this particular vertex. So you can play, this is definite contribution sum. Now what we can do, instead of gluons you can put photons. Okay, instead of gluons, what is the time now? You can do the same thing with F mu, F mu. Okay. So what it will lead to? So you have an operator. Maybe I'll write it down. So what you have is a production mechanism in standard model. Now you also have a discovery channel also, H2 gamma gamma. Okay, everything will have a correction in assembly. Okay. This diagram is also possible. Same to same, you can write it down. Okay. Okay. Now, okay, we'll do the further classification. Okay, I'll just finish the photon, and then we'll do the mixed effects and electroweak precision in the next class. So, in the standard model unbroken language, you write it as B mu, and then stagger H goes to E square. So this gives you a correction to alpha goes to alpha em sm 1 plus ch gamma v square by lambda square. And then you also have a new correction. Oh, sorry, photon. Which also has very similar like thing. Oh, there is no v is v by lambda. Vertex, effective vertex. Correct, lambda square, yeah. Coupling should be dimensionless. V p mu lambda square, that's what. It won't give mass to the photon. Why it will give you mass to the photon? Gauge invariance will forbid it. Photon mass will never get mass because it's all gauge invariant way. Okay, you will never get mass. Just the diagram will not help. It cancels it. No, yes, mass. Higgs couplings to photon will not give you mass. This is the broken phase. This is the broken phase. This is the coupling with p mu p derivative coupling. It is not m gamma square gamma b mu term in the Lagrangian. Remember, this is not this term in the Lagrangian. You are thinking in terms of a fermion mass term. It's not a fermion mass term. The bosonic mass term should always go as m square b mu in the Lagrangian. It's not contributing to that. It's a completely different term in the Lagrangian. Okay, which is del mu b mu or this term in the Lagrangian. right? Yes, yes. The P's will go linear in P, right? Same as scalar QED. Same thing happens in scalar QED. That's the reason I insist on scalar QED a lot. Yeah, I like the theory very much, but anyway. So, so what we have seen now, the remaining left is the Z bosons and the mixing that we'll do in the next class, and the effect in SME, electrical precision test. Okay. So you see SMEFT, it looks so simple, but in the broken phase, it modifies so many things. Okay, it modifies the couplings, it modifies the wave functions. So you have to canonically renormalize them if you want to do any field theory in SMEFT. Okay, when people say that they can do loop calculations SMFT, you have to be very careful whether they are canonically normalized wave functions, brought the propagators in the correct basis or not. All these things are issues. That's the reason why on-shell basis is much better compared to. So I'll stop here and we'll continue in the next class. Tuesday. Okay.